Good morning. My name is Darren Miller. I am a distinguished technical marketing engineer. The room capacity was registered at 182 people. The number of people who registered for the session was 182. So there might be more people coming in, and you'll need to get nice and close to one another. Maybe you'll find somebody that you can have a beer with later tonight at the customer appreciation event. Hopefully you're here to talk about security group tags. Is there anyone in the room who's not here for security group tags? Good. We're starting off the day wonderfully. So they put me in this slot, and I use this joke with the gentleman in the front. They put me in this slot because this is normally noon. You eat, you take a nap. Well, I will put you to sleep. You'll have a great day. You'll have no problems taking a nap if you would like. I won't be offended if you do. But what we are going to talk about today is a detailed walkthrough of security group tags and how you can adopt this technology. And I'm going to be showing you how people have deployed it in incremental fashion. So one of the very first things that I would like to do, if I can get this clicker to work, is encourage you to ask questions in WebEx Teams. We will have a question manager in the room. She is not in the room at the moment because she's going to get more of these lovely giveaways. It is a sock that you can wear that has group-based policy on it. If you want that, you can have it. I personally don't have a pair, not judging the socks. But she will answer questions in the Teams room. They asked me to introduce myself. So basically, the takeaway from this slide is I've been at Cisco a long time, and I've gotten heavier and older. Basically, in order to combat that, I drink healthy things like beer, and I run a lot. So I'm an avid runner. I've done 10 marathons, about 50 half marathons. So one of the things that has led to, though, is that I have been classified, and this is a word that you will hear in the presentation, by one of my peers. And he has accused me of being a beer thief. Now, the problem with that accusation is that in the picture he took, where he accused me of being a beer thief, that was the beer that was put in front of me. Now, I don't know how it works, all over the world, but typically when the beer's put in front of you, that's yours. But better yet, I paid for it, which in most parts of the world means that was my beer. So the key to this is you have to classify things properly to get what you want. So that really doesn't make me a beer thief, it makes me a beer lover. So that's the start of this presentation. Now, it'll get better, I promise. So, the agenda. I'm going to do a very brief review of security group tags. In the abstract, we encourage you to have a base understanding of security group tags, but invariably people do get into the session that do not. So I'm going to go through that, but it's going to be relatively quick. If you have questions about it, I will happily take questions in the session. But if I think it's going to delay the session too much, I will defer them to the end or to the WebEx Teams because I do have a full agenda. Then I'm going to talk about use cases, and I'm going to start in the campus and show you a pattern that you can replicate out into the WAN and into the data center. And it basically gives you a set of principles that are repeated in any kind of deployment. But then I will talk about a WAN deployment, and I'll talk about integration into the data center, right? So that's our agenda, and at the end, hopefully you will have had a good nap or you will have learned something. And either way, we'll summarize and you'll go on to your day so that you can get ready for the customer event tonight. Sound reasonable? Everybody ready to go? Now, I am an energetic young man, so if I talk too fast, let me know. I'll slow down. But what we want to talk about is if we look at traditional segmentation, and a lot of people are trying to address the problems of traditional segmentation. We typically have had in networks two kinds of classifications, one for voice and one for data. But as we've had numerous different waves of worms or malware or whatnot, people have wanted to introduce new classifications into the environment in order to control or limit the area of impact of the different kinds of either directed attacks or automated attacks via malware. So when they do that, they typically have created a VLAN per classification, right? And that's fine, that works fine, but it has a bunch of things that you have to do in addition to that. You have to create the VLAN on every aggregation layer. You have to allocate IP addressing. In some cases, if you're introducing a new classification, you might have to readdress. You also have to implement DHCP, and this works fairly well in a single site or in a small number of sites. But as you proliferate this across a global environment or even a large-scale environment within a country, you run into situations where you create high cost, and it's very manual. So this was one of the major downsides to traditional segmentation is you'd have to extend the VLAN concept across the networks manually, right? And you would have to extend the classification for the ACL, the IP address or the prefix, manually. So what we've been asked to do is to create abstractions and focus those abstractions on virtualizing the network component, which I'll talk about in a bit, and virtualizing the security classifier. So the security classifier is the security group tag. You may also hear it referred to as the scalable group tag. Can anybody for a pair of socks tell me why they renamed it the scalable group tag? Nobody's going to answer because nobody wants the socks. Oh, here. The answer was the RFC, and that's close, but that's not the actual answer, but I'll give you the socks anyways. Oh, you already have the socks? Oh, okay. Well, so the real reason was because the security group tag is going to be used for more than just security, right? The scalable group tag has been used to influence routing, so there's policy-based routing on the standalone platforms, and QoS. There's SGT-based QoS within the standalone platforms and within software-defined access. But the key to it is in either scenario where you're trying to influence a network policy, you need to be grouping like devices on attributes. And those attributes can be something as simple as user groups or a guest environment. They can be sophisticated attributes. Whoops, that was not supposed to go. They could be sophisticated attributes like saying, is it my user on a managed asset in a compliant state, right? The identity services engine can answer those questions for you, but it doesn't have to be our engine that does that. Any engine can answer those questions. But that is an example of how we could classify, guests or using profiling build-up management systems. But we also need to classify the other end of it, a communication, so applications and workloads, in order to build a security policy. And once we've done that, what we can do is we can instantiate what we call a topology-independent security policy. What it means is that no matter where in a network that you instantiate the policy, that policy will take effect. And we represent that in one of the products that you'll see in a matrix or a cell format. And basically, you define the source, you define the destination, and then you define a permission in between. That permission could be an ACL, it could be a quality of service definition, or it could be a pathing selection within a WAN fabric, as an example. But the key is we want the policy to follow the user throughout the network, and as we add new classifications, it becomes a centralized controller function, not a distributed function in the network. And the reason we do that is we're trying to keep the operational expense of adopting new classifications to be much lower than in previous scenarios. So if we start implementing this policy, we can start discarding traffic no matter where the endpoint lives within a managed environment, right? And that's the key. This is a managed network technology. You're not going to use this at Starbucks unless you VPN back into a managed environment, right? But we can start making these decisions for users on any endpoint going to any workload that you manage, whether that is in a traditional data center or within a public cloud infrastructure as a service offering. And no matter how that happens, if you move between locations, that policy follows you. It doesn't matter. So there's never a move, add, or change necessary for when people are reallocated within a building, or they move floors, or they move physical locations, or you acquire a company, or you spin out a company. The policies will always be in effect. And what that gives us is the ability to really lower operational expense, and I'll show you some figures that we have there. Now, the key to this is there's two different ways that you can classify, right? I was classified as a beer thief. I did that wrong, right? I'm really a beer lover. Remember that if you're at the party tonight. Now, We do this in two ways. A dynamic way, which is automated by computers, right? You either do it through the Identity Services Engine, you learn it through ACI, or you learn it through some third-party controller. That's a dynamic classification. And typically, that is the predominant way people classify within the network. But there's also always a static component where you are going to make a decision as an administrator and you're going to key a static classification into the controller and the controller will distribute it into the environment, right? So you always have those two different types. Now, if we have the architecture working optimally, what we want to do is classify at the ingress of the network, in this case the campus access, and we want to filter at the egress of the network. So that means we have to transport the tag across the network. And I'll tell you why we want to do that in another slide, but we first need to understand the transport of the classification of the security group tag. So there's two ways to do that. There is a control plane, and the control plane is something that we call SXP, Security or Scalable Group Exchange Protocol, and it communicates basically a simple IP to SGT in a TCP channel outside of the data plane traffic. So the frame from the endpoint comes onto the network. It is not modified, right? There's nothing done to that frame. It's sent through the network. Out of band of that, I communicate the IP to SGT, in this case, IP to 50, through the network to the first device that is capable of carrying the tag on the frame or the packet, right? So that's what we refer to as inline tagging. So it's a hardware capability or a software capability in a particular device to be able to read and write those tags and do something with them. And then we would carry that, in this scenario, into an Ethernet frame, carry it across the network to the data center, and then optionally, we can encrypt the packet with IPsec, or we can encrypt the packet with MACsec. So if you have worries about people tampering with the frame or the IP to SGT in transit, you need to protect it with a traditional mechanism like IPsec or MACsec. And we have a variety of ways to do this. We have enterprise networks, we have GetVPN, internet networks, we have DMVPN, we have SXP and as well as VXLAN because of software-defined access. What is missing from this slide? Anybody? Anybody? Come on, I'm trying to keep you awake here. I was joking about taking a nap. Anybody? SD-WAN, there we go, thank you. SD-WAN is not on this slide. It will come up in a little bit. And the reason it's not on the slide is it is not shipping right now. So we will have SD-WAN capability either for SDA in Q2 or for traditional TrustSec in the second half of calendar year 20. So it is coming. Anybody that's investigating SD-WAN can be assured that we will have interoperability. So why do we want to carry the tag end to end? There's the simple answer. The architecture has no problem filtering at ingress. I could filter on the campus access 9300. Why would I not want to filter at the campus ingress on a 9300 in a highly scaled environment? You. That is exactly right. The answer was you have to have all of the ACLs and all of the classifiers on the switch. So that can be done. And I will show you how a customer incrementally grew from that starting point to a full end-to-end tagging environment. But the key is, what is the single biggest thing you want out of Cisco switches on any day? Does anyone want a Cisco switch to be cheaper? Right? But that's the key, right? It used to be some people actually put 6500s in their access layer. 256,000 routes, 8K a TCAM. And that could do a enterprise policy at the access layer. But we've driven down the cost because of the market, and we've reduced the amount of memory that's available in those switches. So you literally, in many instances, cannot instantiate an enterprise policy and have it be scalable and reliable at an ingress. That's not like my opinion, that's just like the physics of the box, right? So I'll show you how you can filter at ingress with this technology. But in order to get optimal scale, what we want to do is we want to classify whatever that is, in this case 5, and we want to carry it across the network. And why do we want to do that? It's because if I can carry it across the network to the Nexus 5K in this scenario, the 5K now only needs to understand a very small amount of information. What is directly connected to me? In this scenario, there are 2 devices connected to them. Because I'm deriving the source classification off of the frame, the 5K doesn't have to have any awareness, any state of anything in the broader enterprise. The only thing it needs is the state of what's directly connected. So it'll look at the fib and say, what is the destination for this? In this case, it's a MAC and a port. And then what SGT is it? And we'll always ask that question. We'll say, do I have the source tag? Yes. Do I have the destination tag? Yes, it's directly connected. And what is the ACL? And then I will make a policy decision. In this case, it is deny. Now, I can make that policy decision on the 9300, but what it means is that the 9300 would have to carry and handle the entire table for everything behind it that it needed to make a permission statement upon. And it can be done for a limited set of tables, right? A limited set of state. So you can ingress filter with this technology, but it comes with a cost. So what I'm emphasizing here is that it is your decision about where to enforce policy to get the best scale and automation out of this system, right? So another thing that we do for scaling the system is if we have a scenario where we have a prod server, a production server on the left switch, and a dev server on the right switch, what we want to do is we want to optimize the security policies. The switch on the left does not need to know anything about the dev server policies, and vice versa. The switch on the right doesn't need to know anything about the prod policies. So what will happen is when we trigger a download of the policies from the Identity Services Engine, we only pull the SGTs in the columns of the SGACL policies that are relevant to the switch. So we don't have to pre-deploy any awareness of the dev server onto the switch that is hosting prod. Now, if the switch actually picks up a dev environment because of a virtual machine or some other reason, we will immediately then download the policy for that dev environment. So that dynamic mechanism allows us to optimally scale the environment and build an on-demand implementation of ACLs into the data plane. So we save TCAM inside of the switch itself. So one thing that I constantly get asked in the review is this open? So I can stand in front of you and tell you that every single component that I'm talking about today is open or standardized. And they say, well, hey, I don't have a switch vendor X or Y or Z that has implemented it. I've actually asked this question. Unless they allow me to go to switch vendor X and implement it for them, which I'm up for, they have to do it themselves. And we had the same situation with firewalling. When we first introduced the technology, all of our firewall competitors said that is a Cisco-only technology. Now all of the major firewall vendors, Checkpoint, Fortinet, Palo Alto, all have an implementation because they were forced to, because your vote matters. Your opinion matters. If this is something that you need to have vendor interoperability, your decisions with those vendors and your voice to those vendors opens it, right? Just like VXLAN. VXLAN never was a standard until enough vendors heard that they needed to implement VXLAN, and then once that happened, then it moved into RFC status. So every single thing in this is open. We've contributed open source. We have communication over a standards PX grid interface in the IETF, and we've published anything that we can. If you have ideas about how we can further open this technology, let me know, and I'll be happy to take that up. That is one of the things I am tasked to do at Cisco, is to get this more broadly adopted in the industry, not just Cisco product. So at this point, a lot of people are like, that's great, wonderful, why is this interesting? So you've probably heard Cisco talk about intent-based networking for a number of years. This is an example of making intent real. And why is that? Because in many instances, what you're doing is you're using a manager, which we are in this scenario, to write an abstraction that is relevant to your business policy. And then you're writing a policy that supports that business security policy. At that point, the manager takes it, converts it into IP addresses, and downloads it to an enforcement point with just IP addresses. At that point, the enforcement point typically produces logging information that has IP addresses and sends it back to your centralized syslog server or maybe Elasticsearch server. And at that point, what do you get to do? You get to write a lot of fun correlation rules to say what that IP address actually means in the overall system so that an operator looking at those logs or analyzing those logs can understand what the intent of the log really meant, right? In this scenario, we are actually instantiating the intent not only at the policy layer, but in the network hardware itself. We show you the abstraction in the network hardware, and we put it in the software logs themselves. So we actually generate that intent from policy definition down to enforcement and then back to policy assurance or analytics. And why is that interesting at all? And this is, for me as a former security operations manager, this is why. The time to implement network changes when you adopt an abstraction technology like this can be reduced by 98%. The IT operational cost can be saved as much as up to 80%. And then what your management probably is most interested in is the ROI is 140%. And the key is, this is not my opinion. This is Forrester's opinions, having gone out and done interviews with customers who've adopted this technology. So for me, the most gratifying thing as a technologist is that I have real demonstrable results for your benefit from the technology that I build. So this is something that is doable and is usable within environments that can give you some very good returns once you get it deployed. So at this point, I want to talk about the use cases and design considerations around those use cases. And I'm doing it in a way that it has patterns, so you can take a base use case and grow that within the enterprise. Before I start that, I want to preface it by saying we will get questions about what if XYZ platform, does it support TrustSec? The answer is I can't write a slide that actually holds all of the devices that support TrustSec. So at that top URL is an up-to-date matrix of everything that supports TrustSec and what capabilities they have. Because there are 3 capabilities: classification, propagation, and enforcement that each platform does support. So that's for your information. Please use it to make an assessment of your environment for the applicability of the technology. That is fundamental key. And I will talk about some unique characteristics of some of the platforms in the presentation. So the first use case I want to talk about is a campus access control use case. This is a large manufacturer. Some of you probably own products that this manufacturer makes. They had 3 problems, basically. They wanted to introduce BYOD into the environment. They wanted to be able to make a decision on how to handle production versus development users on the environment. And they wanted to introduce posture so that they can make a compliant or non-compliant decision on the network itself. So they initially deployed this by saying, okay, BYOD and anything that is personally owned, non-compliant, must go through a remote access VPN tunnel and tunnel back to the headquarters and then get access to a limited set of resources in the corporate environment. But they could do things like unified communications. So it was centralized tunneling, right? But that introduced some interesting challenges. So you would have someone on a BYOD device using Teams to talk to somebody right down the hall that was using Teams, and their traffic would have to go from, as an example, South America back to North America through the tunnel, and then back to South America for the phone call. So the application performance was not optimal. So they started to look at ways to have controls for personal assets, non-compliant, as well as production and dev in a distributed fashion. So the very first thing they looked at was firewalls. They had 4,000 locations. Anybody want to manage 4,000 firewalls? Does anybody manage 4,000 firewalls? I'm sorry. But that was what they started to look at. And so that immediately started them to do analysis of capital expense as well as operational expense. That really did not have what I would call enough ROI to justify. So then they looked at using the wireless LAN controller and implementing ACLs on the wireless LAN controller. Has anybody ever written a long ACL on the wireless LAN controller? Once? Exactly. There's a very limited capability on the wireless LAN controller to implement an ACL, right? It can do it, but it must be a very simple ACL for a simple use case. I have 3 use cases, and none of them are simple use cases. So what they decided to do was take the classification learned on the wireless LAN controller and communicate it up to an upstream device that had security group ACL capability in order to gain the scaling benefits of the abstraction as well as the dynamic download capabilities to keep the TCAM in the switch to a low enough point. So what their design looked like was that they had an aggregation layer up above the wireless LAN controllers and the APs, as well as their switches, and they would send SXP traffic from those downstream classifiers, so the access devices, up to the aggregation layer. And in their branch environments, that aggregation layer was a router, right? But they started in their campus first. In addition, they would statically classify their workloads for dev, as well as other resources that BYOD assets were allowed to get to, as well as non-compliant assets would get to remediate. So if you didn't have the latest patches, we still wanted you to get to the latest McAfee antivirus updates, things like that. So what they would do is they would take the static classifications and they put that into the identity services engine, right, through the UI. But they would rely on the computer or the identity services engine to make the classification for the endpoint. And once they had those 2 things, then they would communicate them to the aggregation layer. Now the aggregation layer has a table. However, that table is localized to the site. So the table on the left side of the slide is not the same table that is on the right side of the slide because they're different IP addressing schemes, right? But they all have the same policies applied to them. So in a scenario where there was a BYOD device that came onto the network and it generated a normal IP packet, that would be sent to the switch that was at the aggregation layer. And at the aggregation layer, for every packet, whether it was a endpoint that was classified or not classified, for every packet, it will do a lookup and it will ask itself in parallel 3 things. What is the source of the packet? Is it on the frame? Is it in the table? In this case, it's in the table and it represents BYOD. Then it will say, what is the destination classifier for the packet? In this scenario, it is the data center. And then it will ask, what is the policy for that match of the source and destination? In this case, it was deny IP. And that is the basic fundamental thing that you need to think about whenever you are looking at enforcing a policy. Whatever the enforcement point is, it must have the source address from the frame or the packet, and it must have the destination address either via direct connection or some other mechanism like static configuration or a protocol like SXP, right? And as soon as you do that, you now have, quote unquote, a line rate firewall or a line rate policy enforcement point. So whenever you see performance metrics of the routers and the switches, it is with a filtering function happening every time. Whether you're using it or not, doesn't matter. A Cat9K is always doing a lookup against a security policy in its pipeline. So whatever the published specs are for the Cat9K wire rate, that's what performance you get out of the ACL. Because it is already being done, it just so happens you're hitting a permit IP on every packet, but it's being done for every packet that goes through the system. So how do we sort of look at this? Well, one of the very first things we have to look at in an environment where we're going to adopt is understanding some base capabilities of hardware. So I have had a customer that said, oh, that's a great design. I want to use that design. The upstream device from my wireless LAN controller is a 3750X. This is literally a switch we don't make anymore, but it is a switch that he had in his environment, because most of you probably have, older switches and routers in your environment. So he wanted to use this. The problem became that the ASIC in that environment, or in that piece of hardware, was too old to actually understand what was going on. And that is because it is from a classification of ASIC that is called a port VLAN ASIC, where all of the forwarding decisions were really layer 2 decisions, and they got extended with layer 3 when routing was introduced. So the core of the ASIC design was looking up MAC addresses and making switching decisions, not routing decisions. So that port VLAN ASIC has limitations in the design I showed you. The other classification of ASIC is what we call an IP to SGT based ASIC, where basically inside of the engine, we're looking at IP addresses to find the SGT. So what does this sort of look like? So in that port VLAN ASIC, as you're coming into the switch, we're going to try to derive the SGT. So the packet might come into the switch untagged, but it's from an endpoint that we've classified with .1x. I will then assert the SGT for the source. Or it might be something that I got from the packet, so I will pull the SGT out of the packet so I can match a lookup. But in these older switches, the only way I can derive an SGT if it's not classified or it's not in the packet is to look in my layer 2 table. So if I'm using IP to SGTs for the source packet, when it comes to me, if it's directly connected to me with a layer 2 connection, I can find the correct SGT. If it's connected to me over a layer 3 hop, what SGT will I derive for that IP address? Does anybody know? The downstream IP router. Because I will have the MAC address of the router in the layer 2 table for that IP prefix. I will not have an IP that I can match to an SGT in that prefix. So I will misclassify the SGT as it comes in. I will find a destination SGT if it's directly attached. If it's not directly attached, what SGT will I find? The SGT of the upstream router. Because I'm going to look for a prefix for a destination. I'll find it, I'll associate that to a MAC address. That MAC address will be associated to the router for the next hop, and I will misclassify the enforcement. This is what I like to call suboptimal. Now that's a little bit of an understatement because I've just bypassed or incorrectly classified the environment and I've applied the wrong policy, right? This is not going to work. But if we look at how we do it in more recent switches, so 3850, 4500, 6500, Nexus 7K, all of these different platforms, including the Cat 9K, what I'll do is I'll look in different areas in the switch for the IP to SGT, right? Again, I'll have it via classification or from the packet, but I'll also look in the layer 3 forwarding information base. The forwarding information base is in a routing TCAM, right? And I'll look in there for an IP to SGT. In the scenarios I've described in the previous design, I will find both the source IP to SGT from SXP that is in the fib. I will then go and try to derive the destination SGT. I will find that through the CLI or SXP. I will have a source destin match. I will look, I will find the correct SGACL, and I will apply the correct policy. Now, there's a very significant point on this slide that is often lost on people. I am storing IP to SGT information in the same fib as my routing information base, right? I'm sharing that memory. So if you're carrying a huge number of routes on your distribution layer or on your core layer, you have to subtract that number from the IP to SGT scalability that you need out of a downstream environment. As an example, Cat 6500 supports 200,000 IP to SGTs. So if I have 100,000 routes in that Cat 6K, I really only have enough space for 100,000 IP to SGTs, right? Now that doesn't crop up and really, become impactful for anyone unless they try to do ingress filtering. And I'll show you that in a little bit. But I want you to keep that in your mind because the fib scaling along with the TCAM scaling of the security ACEs, are multiple dimensions for scale inside of any enforcement point. And this is the case, memory is memory. We're trying to find the optimal place to put memory, or put tables in memory. And it just so happens we typically had big tables for routing that were underutilized, so we overloaded that table for the IP to SGT. And it typically is something that works very well, because down in the access layer, where if we have the right architecture, I only have the fib entries for what's directly connected to me. I don't have a huge routing table. I might have a default routing table, where I might have a smaller routing table in that access layer. So the implications of this is, if you try to use a port VLAN ASIC for an SXP receiver, listener, that receives IP to SGT bindings, if it is not only enforcing on directly L2 connected devices, it will misapply the policy. So in essence, in most environments, it is not capable of being an SXP receiver and being an enforcer. Now, these switches can tag and they can communicate via SXP, so they can be a classifier and they can be an enforcer if you have inline tagging, but they do not do well if they're listening to SXP. And that is the main takeaway that I would like you to have from this part of the discussion. But it does impact other parts of the portfolio. Nexus 5K, same thing. The 3560CX, the IE, intelligent Ethernet, industrial Ethernet switches that are put in manufacturing lines. These are all inline capable, but not able to be SXP listeners. It's very significant, because I've been in manufacturing environments where people have tried to use the IE switches as SXP listeners and enforce policy, and they're just not capable in the hardware, right? And then they're like, oh no, my entire design is not worthwhile. So you have to understand some base capabilities before you start your design. So at this point, I just want to show you how you configure this, because from a base configuration, you work out from there. So in the wireless LAN controller, because we are using SXP, what I'm showing you is that I basically enable it. Well, hey, my pointer is not working. So I will use my hand. So I'll enable SXP. Then I will define my peer. So I'll basically tell SXP where to talk to and where to replicate its local table upstream to the aggregation layer. And you can see in there, the peer address is 10.1.44.1, my source address is there, and the connection status is on, right? You can configure that, and then you can see on the other side where, for an individual client, I'm actually assigning a tag and displaying it within the UI interface. So now I've actually established a connection to the upstream switch. But on the upstream switch, I also want to take into consideration the other access layer, a wired switch, and configure the upstream switch, the aggregation layer, as what we call a receiver or a listener. So in the top, I have a 3850 where I, again, define a peer and give it a password, and that's all I do, right? On the upstream Cat9K, what I do is I define downstream peers, and instead of having a local listener or local speaker, I'm defining them as listeners, because all I want to do is hear from the downstream devices, right? And then in the upper right, I can see on the 3850, I have a classification of full access, while my wireless LAN controller had a classification of BYOD. I can see that both of my downstream peers are on through the show CTS SXP connection command, and then you'll see the aggregated table. The BYOD in that table on the lower part of the screen came from a wireless LAN controller, and it aggregated that with the full access that came from the access switch. So at this point, I'm building that table automatically through the SXP protocol on the aggregation layer. Now, if either one of those devices generates traffic through the aggregation layer, I will now be able to derive the source address and the source SGT from that. So while we're doing that on the access layer, all we're doing is communicating IP to SGTs. We haven't actually hooked that aggregation enforcement point up to ICE. So I have to do a few things in ICE. The very first one that we want you to do is we want you to assign the device what we call a TrustSec network device SGT. The reason we want to do that is we want you to write policy so that the TrustSec device always can talk to ICE. Why am I telling you this? Because in the policy matrix, you can have a default policy, and people will always turn on the default policy to deny. So I'm a switch. I want to make an authentication request for a client connected to me. I go to send traffic to ICE. I look up the source IP of myself. I don't have anything. I look up the destination IP of ICE. I don't have anything. That means I've missed all policy, and I go to the default on the matrix, and the default is deny. So what does the switch do? Throws away the packet. What have you just done? You have a big black hole in your network. And depending upon how you've deployed TrustSec, it might be the entire network. This, again, is what I like to deem suboptimal. On my flight over, I had the unique pleasure of troubleshooting an environment where 2,000 switches suddenly disappeared. So, why did those switches disappear from the network? Very first thing, they did not find the network device SGT. Second thing they didn't do is they didn't write policy against it and against ICE. Third thing they did was they turned on default deny when I begged them not to. So I may beg you not to turn on default deny until you're really, really, really sure you want to do it. Because switches are built to forward things, and unless they have explicit classification of what's communicating, even in their control plane, they will drop the packet. So default deny is a very powerful tool. It can be deployed. But if you do not do it without a lot of thought and a lot of testing, you will have bad experiences with it. And my standard line is I used to be 6'5". I used to be about 250 pounds. I used to be a big guy. And the customers have beaten me down to this size because of those kinds of mistakes. The technology worked perfectly. But what I'm emphasizing here with that, very joking comment is that you have other things to consider than just the technology when you're making these policy decisions. And it's very important that you make those considerations, okay? Because it will save you a lot of headache, it will save me a lot of headache. But the good news is I now no longer handle those calls. My colleague in the back, Fei Lee, she handles all of those calls now, so I don't have to worry about it anymore. So after you do that, what we want you to go do inside of ICE is we want you to assign that TrustSec SGT to what we call the network device authorization and assign it to the network. In addition, a best practice is I want you to go into the EAP fast settings, and you'll ask me, why do I want to go into the EAP fast settings? Because when the device reaches out to ICE, it's going to authenticate itself and authorize itself via EAP fast, and it will use something called a protected access credential. And if the protected access credential expires, it will go through a whole provisioning process, and you'll see a whole bunch of events on your network that you might not be expecting. No outages will occur, but in order to avoid that and having you to open a attack case and ask why did I get all these logs all at once from every device everywhere, I suggest that you set it to a very large number and try to ignore it as much as possible, because it really is a self-provisioning mechanism. It has no operational impact whatsoever. So after we do that, in ICE, you have a network device definition. In that network device definition, you have to tell it that you are speaking to a TrustSec device. So you will see that I have a device ID and a password. That is part of the mutual authentication I talked about with EAP Fast. In addition, you will see that I have a number of different timers that are available for re-authentication. They're available for how long to keep environmental data, which is something I'll show you in a bit, as well as how long to keep the policies. You'll notice that I'm recommending that you set those numbers very large. These are not defaults. Why am I telling you to set these numbers to be very large? How many of you like the switch updating a policy that you have sitting in the policy server without you knowing it? Anybody have things called change control windows? Anybody? Right. So people want control about when a policy goes out. So we recommend that we set these very high so that you have control of when they go out. When they go out, when you do update a policy through a centralized push, the number or the timer gets reset. So every time you push, that timer resets. So if it's set for 365 days, unless you've not touched the policy for 365 days, you will not see an update on the network. And that has happened. So, missed something there. COA, you can notify the device through two different mechanisms. One is what we call radius COA, and the other is through CLI. The reason you use COA is for normal moves, adds, and changes of policy. It is very quick and it's very efficient. However, in some scenarios, you may be talking to a device that does not support radius COA, so very, very old Nexus 7000 code, or if you want to make a bulk update, meaning you've changed everything in the policy, you will find that a CLI refresh from ICE does all the work for you. It goes out to the device and issues the CLI. You will find that it is far more efficient and will be faster than using COA. So what do I mean by that? I have a customer that had a 200 by 200 matrix. They issued an update from ICE via COA. It took approximately 4 hours to do the update. Their change control window was 2 hours, too long. So they were looking for a more efficient way. We changed all their updates to CLI. Their entire update finished in 30 minutes. So dramatically faster when it's a large update. If it's just incremental updates, radius COA is just fine. So now we have to go back to the aggregation switch, and we have to do a couple things. We basically have to turn on AAA, and then in the radius server definition, we must have a PAC keyword. That is telling the switch that it must authenticate to ICE through that EAP-FAST protocol. In addition, we must have what we call a CTS authorization list. This is basically a list of IP addresses that it needs to go to at initial boot to download all of the environmental data about the TrustSec environment and download the policies. This can be a completely different AAA server from normal authentication that you're doing with Radius. So if you have a third-party device, I'll show you how you can authenticate via the third-party Radius, free Radius, whatever it might be, but still download policy from ICE, and that is the key to doing that. Then you add in some authentication and authorization commands, and then we have to put in a couple commands that are legacy commands, .1x at a system level, and then until we enter the credential, until we enter basically the device ID and the password, I have not spoken to ICE. Because without this credential, I will not talk to ICE. But once I do enter that credential, then I will talk to ICE and I will get two things. One is the protected access credential, and the other is the environmental data. Now, in this environmental data, there are two things that you need to look at. The very first one is there's the device SGT, and then below it, there's what we call a server list. The device will no longer listen to the locally defined Radius servers and will use this list of Radius servers instead. So some people love this feature and some people hate this feature. Depending upon your operational preferences, you may love this feature, you may not. And I will show you how you use it, especially in a load balancing environment shortly. So after we've done that, now we have the device talking to ICE. Now ICE needs to actually create the SGTs and assign policy. So we go in and you can see that I have ACI EPGs represented in my SGT list. That is to show you that you can create this through APIs, so an automatic creation between ACI and ICE, or you can hit the add button and define it locally. So you define the groups or the classifications within the environment. Then you're ready to define policy. By default, we put you into what we call a matrix. It looks like a spreadsheet. You will double click on a cell, just like a spreadsheet, and you will have this pop-up where you can see the source and the destination, and then you can sign a permission. These are stateless ACLs, right? This is not a firewall. We can interoperate with firewalls, and I'll show you how to do it, but that is a stateless ACL. But what is it in that ACL that you do not have that is going to be applied across your network? do not have the IP addresses. There's no source IP, there's no destination IP, right? Once you have that defined, you're now ready to deploy that to the network. Now, one thing to call out here, I am showing the ability to have multiple ACLs within a cell. By default, we have turned that off. The reason that we have turned it off by default is that wireless LAN controllers, Airspace OS, as well as Nexus, only support one ACL for an SGT and a DGT. So we've turned it off so that you can't have multiple ACLs in the matrix and have those devices error out. So by default, if you pick up ICE 2.6 or ICE 2.7, you will only be able to put one ACL, so you need all of the policies in that ACL. You can't use it like an object builder and layer multiple ACLs with Airspace and Nexus products. If you're using iOS XE, in iOS XE only, it does allow that. So that's a little specificity that you need to know. So once we have this, then we're ready to go back to the aggregation layer, define, in this scenario, I'm just using CLI to illustrate it, define the prefixes for the destinations that are in the data center, right? And until I issue the CTS role-based enforcement commands, I will still be passing traffic. Even though the device has the policies, even though the device has the table, the IP to SGTs, I won't enforce policy until I turn on the commands, CTS role-based enforcement. Please note, the second command allows me to turn it on a per VLAN interface. This is very significant for anybody who wants to test the technology without putting it everywhere. So you can incrementally turn it on at the aggregation layer for only a particular set of customers or set of clients. You do not have to deploy this across an entire box by default. So I'm going to show you that I'm manually refreshing the policy. So in troubleshooting scenarios, you would use CTS refresh environmental data because you want the new SGTs, and then you want to refresh the policy, so you download the new policy. If you are in ICE and you hit a button to deploy, that would be handled for you automatically. I'm just including this for your reference. So if we go look at environmental data, now we see the server list, but we also see all of the SGTs that we've defined in ICE. And the reason we're downloading that environmental data in this SGT name table is because we want the ability to map the number to a name that's human readable so that when you're operating it, you actually understand what these numbers mean. What was the biggest complaint about IP addresses? The numbers were not human relevant. Now we have numbers that have a human relevant definition that you can read. So it's very important. So I told you I'd explain the TrustSec server list, right? So this is controlled in ICE, so it's centrally controlled, right? And what you can put in there, by default we put in every PSN in the list and the real IP address in the list. How many of you run server load balancers in front of your Radius servers? Anyone? Few people? Okay. So most of the time, people have configured the network device to speak to the virtual IP address of the server load balancer, not to the real PSNs. So they often want to enter the virtual IP address of the server load balancer here to continue to force traffic for downloading to the PSNs that are also serving client environments, client authentication, 802.1x, MAB, those kinds of things. That is entirely your decision which model to use. So basically what it looks like is if you enter the virtual IP address into the device, into that server list, the server, when it goes to download policy, will always go to the virtual IP and download from the PSNs through a load balanced environment. That is fine. You can use the virtual IP address and just the virtual IP address. However, I have some environments, typically universities, where they are very worried that client authentication at peak hours will starve out the policy download. So they want to dedicate a PSN just for SGACL download. And if you can do that by manipulating that server list and changing it away from the virtual IP to just enter the PSN 4 IP address in the server list. So because of that authorization list, I can split my client authentication traffic goes to the cluster of PSN 1, 2, and 3, and my SGACL download will only go to PSN 4. So some people love this, some people hate this, but that server list is really what is controlling where you go to download IP or the policy. And that's there for your troubleshooting, because a lot of times people will actually say, show AAA server, they'll see the device that's defined in the CLI, and they'll go put a sniffer on it. Well, that's not where we're going to download security group ACL policy. We're really going to the IPs that are listed in that server list. So you need to know that as you do your troubleshooting. So policy push. So let's assume we have a BYOD device. It's communicating to the development environment. I go into ICE, I go to the source destination, and I add a deny IP. At this point, I want a centralized provisioning function to push that out to the environment. So I look at the UI, I see a deploy button, I hit the deploy button. At this point, some people would assume that I've deployed my policy. How many people think that we're good enough UI designers to have that deploy button actually deploy policy? Yeah, nobody does, right? So what really happens is you have to go look in the upper right for a little indicator that says 1, and you have to click on it, and then you have to tell them, yeah, I really did mean to deploy that policy, and click OK. If you do not do that, none of the devices get notified that you have a new policy. So this is something we were trying to fix. We actually have fixed it in the DNA Center UI. So while we're not great at UI design, we do learn over time. So we appreciate your patience with us in that regard. So once you hit that button, then it sends out a notification to the enforcement point. The enforcement point says, oh, I need to update policy, and it asks ICE for the new policy. And you can update policy across your network via this centralized button, right? So you have centralized control of the policies. So how do we sort of validate on the device that the policies are correct? So there is a policy validation button in ICE 2.6 and above where you can hit a button. It goes out to all of the devices and issues this command, show CTS role-based permissions, and basically validates that the policies you have in ICE are the policies that are reflected in the network device. So you'll see a permission from different groups to one another, and you will see that there's a deny IP, and that matches what is in ICE. We'll automatically do that for you from ICE and report that through our alarming dashboard if there are any misses. We assume everything is correct. Question?
You say that's in 2.6. That feature seems to be there in 2.4 as well. Is that because that works in 2.6?
Fantastic observation. The observation is this feature seems to be in 2.4. Why is it in 2.4 and yet you're saying to use 2.6? The observation also made by this gentleman was that does it not work in 2.4? It works in 2.4. It does not work well in 2.4. We do not give you enough information. If you have a scenario where there is enough discrepancies in the network, where like 10 devices do not have the right policy, we actually report that back to the infrastructure. The infrastructure, because of internal issues, truncates it. So we'll only show you 6 of the 10. So if you ask me, does it work in 2.4? I will tell you not in every scenario that you need it to. So that is why I don't recommend it until 2.6 when we report the entire set of data.
So follow-up is, is it supposed to actually validate that the switch is downloaded once it needs, or will it still say, I have a matrix here and you don't have all those policies?
So very good question. So the question was, will this policy validation actually look at the switch and validate it has the right ACLs for the only SGTs that it needs? Yes, that is correct. It does not try to go validate that every SGT is on the device. It is only for the device, the SGTs that are currently connected at the time of the validation. So another way that you can look at this if you want a little bit more detail and you're worried about things like versioning, like what's the right version, is you can do show CTS policy SGT, and you'll see SGT 4-06, employees -01. The dash is a delimiter, and the 2 characters after it is a version number. So if you have updated an ACL, as an example with deny_log-10, that is the 10th iteration on that ACL. And that is also published in ICE. So if you manually want to be looking at these two things, you can validate that the device has the most current version through that identifier, or you can actually look at the ACEs, the access control entries that are in that policy. So this is just an alternative way to look at the permissions and get more detail out of them. Now, people are saying, well, great, I know this aggregation layer is getting the source, I know it's getting the destination, I know it's getting the policy. How do I actually validate that it's doing a function? The first way you can do that is via the log keyword. We will produce a syslog, a rate-limited syslog of the data. And we will give you the interface where the ACL is encountered, the ACL name, the source SGT, destination SGT, and then we will give you one log, and we'll tell you in the logging interval how many times that was hit. We are not a firewall in the switch, right? Switches want to forward. I don't want to starve my control plane and starve routing by pumping out logs. Why do I make this point? And this is a very important point. A switch is not a firewall. If you have regulatory compliance or any other auditable scenario where the auditor expects a firewall, use a firewall with the SGT. I have had a number of different customers with regulatory compliance try to replace a firewall with a switch. The technology works fantastic. It is giving them, 40 gig of access control into a data center. And the auditor will come in, and because he doesn't know any better, he will say, no, I need to see a log of every drop you make. And it will be a hard requirement from the auditor, and do you know what will happen at that point? You will go buy a firewall, and you'll put a firewall in because the auditor told you to. And upper management will consider the project a failure because you had to go back for more budget when the technology was working just fine. But the key is understand the requirements of the policies that you're implementing in order to pick the right enforcement point. It saddens me when this happens because if we had just chosen a firewall for that requirement at the beginning of the project, understood the requirements of these auditors, we could have picked out a firewall that was appropriate for the job. But in some scenarios, we don't do that. And the technology works great, but it is not sufficient for the task at hand. So please try to pick out the right technology for the task at hand. So we also have counters. These counters are aggregate counters for the SGT DGT match. And in the switches and in the routers, you will see software denies and hardware denies, software permits and hardware permits. Basically, 9/10 of the time, you are going to see a hardware deny or a hardware permit. What are things that would generate a software deny or a software permit? Anything that's destined to the switch itself, correct. And this can be things like ping. In many scenarios, people will test access control by pinging the device itself. And they'll then ask the question, why isn't the hardware counter not incrementing? Because we're going up through a software control plane to the general purpose CPU and then responding. And so the increment, anything that gets punted to the general purpose CPU, DHCP, ARP, things like that, they will increment that software permit or hardware permit, or software deny, excuse me. So it's a way to do the monitoring, but I wanted to explain that nuance because that has generated 10,000 attack cases. And it is a simple counter issue as expected. So in the scenario I showed you, I was using wireless, right? But the wireless LAN controllers that they were using didn't support SGT and SGACL at the time. Now they do. So as of 8.3 and beyond, the wireless APs actually do enforcement of SGACLs. Now the key thing here, and the reason I'm showing you this, is it does still use the paradigm of tagging on ingress and filtering on egress. The key is only the APs do the filtering. So oftentimes people will see the SGACL downloaded to the wireless LAN controller and then look on the wireless LAN controller CLI for permits and denies. But that's not where we're doing the enforcement. We're actually doing the enforcement on the APs for scaling reasons, right? So what happens is if I have a device that comes into the network and it generates traffic, The ingress AP will tag the packet, send it across the wireless LAN controller to the other side through the Ethernet over IP tunnels, or the DTLS tunnels, and the other egress AP will do the same lookup that we've done. Do I have a source address? Yes, or a source tag. Yes, it's on the packet. Do I have a destination? Yes, it's directly connected to me. What is the policy for that permit or deny? In this case, it is permit. So that same pattern of do I have a source address or source tag? Do I have a destination tag? What is the policy, right? Those things occur and they happen inside of the wireless LAN environment. Now, since we talked about a campus deployment, something that comes up all the time is what about the Nexus 7000? And the Nexus 7000 has supported SGTs and SGACLs for a number of years, and it generally works. Now, you will note I said generally. Why does the Nexus 7000 generally work? Because there is something called a Nexus F3 line card. The Nexus F3 line card has low-level ASIC restrictions on how it can be configured. It can only tag traffic or receive tag traffic with a .1Q header, whereas the Nexus 7000 very often deployed in environments, in the campus core. How is it very often configured? With point-to-point layer 3 links. What did I just tell you with this restriction? If you want to tag traffic across the Nexus 7000, you will have to reconfigure your interior links and change them from point-to-point IP to trunked and SVI links. Everybody's cool with that, right? Everybody's very happy about that restriction? No, nobody's happy about this. They hate this restriction. They've asked me to fix it. There's literally no way I can fix it. It is a restriction that is baked into the silicon of the chip. It was designed wrong. I can't do anything except apologize for this inconvenience. I am sometimes okay at presentations, so I just told you the worst thing in the presentation you're going to hear, and I will tell you how we can get around this. But there's another thing on this. It does have to bypass CDP, LLDP, and other traffic. In older versions of iOS, the Catalyst switches as well as the routers would tag that packets. So you basically had an interoperability problems between switches and routers with the Nexus 7000 F3 line card. F2s are fine, M3s are fine, you know, anything else except the F3. But the F3 was very, very popular because it was cheap and it had a lot of port density. So it is all over the networks. So we do have a fix in iOS XE 16.10 that allows the switches and the Catalyst switches and the routers to communicate to the F3 line card by bypassing, tagging these different control plane protocols. You still need a trunk port. There's no getting around that. So if you have the option and you have an M3 line card, you can set up a normal point-to-point link on the M3 line card, but you cannot do it on the F3. All of that is documented in the URL that was on the previous slide. This is how you do the configuration of the inline tagging on a Nexus platform. The SXP commands are exactly the same. So you go in, you issue a command called CTS manual, and basically you are saying that you're manually tagging on the link. There is an option to automatically tag via .1x, but nobody deploys it for very good availability reasons. If the AAA server is down, we do not bring the link up. Everybody wants to rely on ICE to bring links up, right? Okay, a couple people expressed their dissatisfaction with that. So that is why in 99.9% of the cases, we are issuing a manual command to tell the interface to tag. So we define policy static, and then we tell the switch the peer SGT definition. And then we tell it a very significant thing. We tell it to trust the peer. That is the keyword to allow it to send traffic to me. If you do not issue that keyword, you basically are saying that you're going to classify the traffic and enforce traffic towards this port, i.e. a server port, but you're not going to trust it to send you traffic, right? So if you are doing switch-to-switch links, you must have that trusted command on the inline tagging interface. So I want to go through some common issues that you need to look for. This is not a troubleshooting session, though I want to ask a question. If there was a 4,000 level session that was going through the low-level troubleshooting of all of the platforms, would anybody in the room be interested? Few people. Okay. We do not have that because that can take an entire session unto itself. All of the 9Ks are the same, but the 4K is different from the 6K, which is different from the 7K, which is different from the routers. So basically, in the system, the most fundamental component that you will have on the switches is something called IP device tracking. In iOS 3.x, it was enabled by default when you turned on authentication. So I will have people that will migrate a config from 3.x to 16.x. They will try to turn on TrustSec and they will say, your switch is broken. It's not broken. We gave you the option to enable IP device tracking in 16x manually. And why did we do that? The reason we did that is we needed to converge the device tracking tables for IPv4 and IPv6 into one table. And so the new device tracking that was introduced in 16x needs to be turned on manually. It has definite advantages over the previous version, so I'm not trying to disparage the feature, but it is something that you have to enable manually. As soon as you enable it, you will typically start to enforce policy. So I'm going to show you a scenario where it's functioning and tracking a IP address. So I just do show IP device tracking all. You can see that I have a 10.0.0.1 and a VLAN, so I have the ability to track the MAC address to an interface in a VLAN. And then later in 16x, we change it to take out the IP device tracking because now it's agnostic from v4 to v6, and I see the same thing, right? So that's just a difference in the way you display the command. So that allows us to generate the IP to SGT that is locally authenticated on the switch, right? So I have a total number of bindings. So the reason this is so important is if there's any error in IP device tracking, this bug has long since been fixed. One of the issues that you can have is you'll notice in the top, I have a neighbor discovery, an IPv6 ARP equivalent, that is mapped to the MAC address. And then I have an ARP for 10.0.0.1 that's mapped in the MAC address. And then you'll see in the lower table, the neighbor discovery has gone stale. As soon as the neighbor discovery went stale, the IPv6 component in that device tracking table notified what is called the CTS role-based manager. And the CTS role-based manager, by being directed, removed the IP to SGT. So literally, on a network, they were testing, they went out, they were testing, everything was working. 5 minutes later, all of a sudden, it wouldn't work anymore. Packets were being denied that should be permitted, things of that nature. And what basically happened was there was the bug, and you would actually remove the IP to SGT when neighbor discovery timed out. IPv6 wasn't even being used in the network. So the simple fix in this scenario was turn off IPv6 tracking. We had a simple workaround. We implemented it, and away we went. But the key is the very first place you start with any SGT problem is go make sure IP device tracking is working properly. We did a rough estimate, 60% of the attack cases involving SGTs and SGACLs were somehow related to the change from 3.x to 16.x, and that's why I'm using it as an example. So a couple other things to consider. If you're having SGACL download errors, which many people do, we have a series of things that we want you to do. We want you to make sure you're downloading from the correct server in the server list, right? We want you to validate the pack. We want you to make sure you're seeing the actual detail information in the environmental data. Some people have implemented SD-WAN, and SD-WAN is not doing the MTU and the fragmentation properly, and so you will actually see partial downloads. If you see partial downloads of ACLs or environmental data, go look at the MTU immediately. By default, we set the DF bit in ICE. The software-defined WAN routers do not like that, and that's not just Cisco routers, that's a number of different vendors' routers. They do not like the DF bits being set, even though we're just an application, right? And they should be able to handle that. The other thing to look for is if there's a formatting error in ICE. So when we enter that ACL, it is a freeform text at the moment. We've improved that in ACA where we've built a model, but you could have a formatting error in that ACL that will cause the switch to throw it away. And finally, if you want to go into a bunch of detail on troubleshooting the different platforms, a colleague of mine has created a very nice troubleshooting guide that is on the Cisco communities. So that is one way to do the use case in the campus for that particular customer. Another way that they could have solved the same problem in a very similar way is with software-defined access. Has anybody here ever heard of software-defined access? Cisco hasn't put much emphasis on it. So software-defined access is basically the ability to use the VXLAN endcap to carry not only the SGT, but also a virtual network identifier. That gives us an additional level of policy that we can invoke inside of an environment, a virtual network abstraction away from the underlying topology, rather than having to stitch VRFs through an entire network. So you can create these virtual networks. They're basically VRFs, but they're enterprise-wide VRFs or campus-wide VRFs. And that can be a grouping of building management versus campus users. But inside of the VRF or inside of the VN, you still use the SGT to control policy within the VN and between VNs. So the SGT is still very relevant for granular control. The macro control is not very granular. You are basically making large decisions on IP addressing. In this scenario, you still have the abstraction for the security group tag, so you can make micro decisions. So what is interesting or unique about SD access? Well, one is it uses a Lisp control plane, and that is relevant, and I'll tell you why in a bit, at keeping the number of routes at the access layer to a minimum, because it's a pool model. The other thing is the VXLAN header is an encapsulation inside of IP and UDP. So what this means is I often get to ask, what if I have XYZ vendor as my aggregation layer? Or what if I have XYZ vendor as my router? How do I go over the top of that device that does not understand the SGT? This is a way to do that. You can go over these devices, and they only see IP, so they forward the packet just fine, but we carry the VN and the SGT inside of the VXLAN header in order to allow us to scale out the virtual network and the SGT abstraction. So in the scenario where SD Access is the manager, you are managing policy from DNA Center. And it interfaces with ICE in the same runtime design that I talked about by basically hitting APIs. So if I define a policy in DNA Center where I define two groups and say permit, and then I hit save, as soon as I touch the save button, I go to ICE via API, write those new policies, and then send that deploy button and the OK button all at the same time. So you have one button to press to actually deploy rather than making you do two. So then the policy will be downloaded to the devices, right? So DNA Center becomes the policy administration point in this scenario. This is an example of what DNA Center looks like. One of the reasons that I'm emphasizing this is we've made advancements in the performance of the matrix. If anybody's used a matrix before with a large number of SGTs, it can be very slow on ICE. Because we are using a relatively new web toolkit, the performance on DNA Center, and being able to navigate through a very large matrix. We've tested to 10,000 SGTs, and we've got some very good user feedback on the scale of it. It's very quick. You can easily navigate a very large environment. In addition, you have a new slide out. Instead of double-clicking and seeing the ACL, you will see the ACL in a slide out as it comes out. It is the exact same ACL, except it is only expressed in models, meaning that you can only use objects in the UI. So that immediately gets rid of the scenario I just highlighted, which was an improperly formatted ACL in ICE. So this moving to a model-based infrastructure allows us to avoid that. There's also other views, list views inside of DNA Center. There's demos all over the place of this that you can see, and this has been shipping as of 1.3.2, which is about 5 months ago. So DNA Center does all of these different things, and you can stack contracts. Now, how does this sort of work? So the key here is that Nexus 7000 with the F3 line card can be in the core of your network. This is the good news portion. Remember I told you the bad news? This is the good news. So what happens is when the full access user comes onto the network and sends traffic to the contractor, the very first thing that happens is a routing lookup to determine if you're in the same virtual network or in different virtual networks. And it does that by talking to the Lisp mapping server. I'm not trying to tell you all the ins and outs of how SDA works. This is just a relative example. So the Lisp mapping server will say, please encapsulate that packet and go to SDA Fabric Site 1 with a delimiter that is the remote switch IP address. So we encapsulate the packet as it goes through the network with the SGT. We go right over the top of that F3 line card. We go over the top of that HP switch or that Arista switch. They don't need to know anything about the SGT. And we deliver the packet to the remote egress point in the network. At this point, what does the switch do? Looks up the source. It's on the packet. Looks up the destination. It is in the directly connected fib, looks up the ACL, and you immediately have a policy applied. So this is just a reference of the configuration of SD access. You can configure this manually, though whether you would want to or not is a different discussion. It's very easy to enable IPv4 SGT. You can also enable IPv6 SGT as of 16.9. So you can connect it. Now, when I've presented this before, people have often said, hey, I have a single SDA fabric. It's working in a proof of concept, and now I want to expand it. How do I interconnect different fabric sites? So traditionally, we've had to strip off the SGT and go across a normal VRF Lite or MPLS VPN network. As recently as 1.3.1, we have introduced a new capability called SD Access Transit, and the little star there, because SDA will be the first interoperability with SD-WAN, we will now be able to transfer the SGT across to SG-WAN in Q2 of this calendar year. I'm allowed to say it because it's within 3 months. So within 3 months, you will be able to connect SDA to SD-WAN or use SD Access Transit, which is currently shipping, to communicate the SGT. Now, SD Access Transit is using Lisp as a control plane to communicate. So when the switch on the left wants to find the egress, he goes to his border router. The border routers talk to a transit control plane. We then determine that the encapsulation needs to go all the way to the right. And then the data plane looks the same. I have a VXLAN header. I have an SGT inside of that VXLAN header, and it's carried across the WAN network. So when we have that same use case, it looks the same no matter if the sites are directly connected or indirectly connected. So I will put the tag on the packet, I will carry it across the WAN, it will get to the egress point, and I will perform the exact same lookup that I did before. Now, the key point in that transit network, the MTU must be able to accommodate the VXLAN header. The specific MTU you need is 1588. Generally, we're recommending to any transit providers that it has a 1600 byte MTU in order to accommodate the VXLAN encapsulation and the SGT and the VNID. So that's a very common question that I get. So in many instances, people are saying, hey, that's great. These virtual networks are wonderful, but if I have an IoT network and I have an enterprise network, I want them to go through a firewall. So some very basic things about firewalls. You can use any firewall, and they can be a non-SGT aware firewall. You can actually attach people to IP address pools, so an IP prefix, and you can build your objects that way if you would like. If you don't want that, if you want to use an SGT aware firewall, the good news is Palo Alto just recently announced official support. They've supported it for a number of years, but it was not official. They recently officially supported it. Fortinet supports it. Firepower Threat Defense Appliance supports it, as well as ASA. So for the most part, the majority of the firewall vendors on the market support this. If you have a firewall vendor that doesn't support it, just tell them to join the PX Grid program because it is an open standard. So we can build the policies on the SGT in those firewalls. Now, what you're going to be doing in an SDA environment is you're going to translate the routing protocol from LIST to either BGP or some IGP, OSPF, et cetera. And you're going to need to be able to do that. Now, the key that I'm showing is the data plane is VXLAN inside the fabric, but then it needs to be VRF light outside of the fabric, so .1Q. You can tag to the firewall if you would so choose. But there are scenarios where the tag will not buy you anything, which I will now describe. So in a scenario where you have, inter-VN or remote connectivity, what does a firewall need to do? It needs to get the scalable groups or the objects for both the source and the destination. So almost 100% of the time, the firewall is actually communicating to ICE for all of the IP-SGTs, either through PXGrid or SXP. So in that scenario, there's no real benefit of tagging to the firewall, right? Because the firewall is going to receive the IP to SGT and reclassify as it forwards the traffic. So what's this scenario look like? So let's say we have an application in the data center. ICE can learn that from ACI, from a static mapping. We will tag the packet in the fabric. We'll send it to the border router. The border router will strip the SGT. We're not going to lose anything because that table is delivered via PXGrid. So I'll look up the source, I'll look up the destination, and then I will look up the policy and I will permit this scenario, right? Fairly standard stuff. But I also can do this between VNs. So again, we'll tag the packet, I'll send it to the firewall will strip it, the firewall will again do that lookup into the table, and then apply a policy. Now at this point, people are typically looking at me very confused, and they're like, Darren, you just showed me all of that. Why are you emphasizing this? Well, it's because prior to FTD 6.5, so Firepower Threat Defense Appliance 6.5, the FTD appliance could only use the SGT to look up the source address. So in a scenario where you're going from VN1 to VN2, and you send it to an FTD running 6.4, guess what it would do with the packet? Anybody? Anybody? Throw it on the floor. So again, this is what I call suboptimal. It does not give you the outcome you want. Now, the good news is, as of 6.5, shipping as of last year, we have the ability to look at the SGT and the destination group tag. And you're now looking at me saying, wait, I know Checkpoint has had this feature for years, and I know the ASA has had this for years. Why is the FTD now just getting this capability? Because we did a poor implementation prior to 6.5. That's why. So you just need to be aware of it. It's fully functional. It works just fine. So at this point, I often get the question, hey, wait, what about switches that do not support the SGT, and what about third parties for the radius authentication? So we support both. Now, in scenarios where a downstream switch does not support the SGT and we want to create an IP to SGT binding, how do we do it? So basically, inside of the transaction for authentication, where we're going to ICE, we can derive the IP address from radius accounting and associate that with state information we have in ICE to build an IP to SGT binding, and then communicate that to an enforcement point upstream that can use the IP to SGT for an enforcement point. So any switch, whether that be HP, whether that be Arista, that can give us the correct radius accounting information, we can create an IP to SGT and send it into the network. Now, for anybody who is a Meraki customer, they have recently announced on the MS390 and the MRAPs that they will be doing something called adaptive policy. Adaptive policy is a normal Cisco marketing term, meaning it's the same thing as SGTs and SGACLs with a new name, because every policy, every group has to have a new name for the same function. But adaptive policy is literally one-for-one SGTs and SGACLs. So we are currently working with them so that they can tag at ingress and enforce at egress in their infrastructure, whether wired or wireless. So the question then moves to, okay, I have Aruba, I have ClearPass, I have an overlay NAC vendor like Forescout. Can they interoperate in this ecosystem? And the answer is yes. And for radius servers, there's two ways. And again, this is operational preference. It has nothing to do with technology. It is purely the way you want to operate. If you want ICE to be the assigner of the SGT and the policy and administration point for all things SGT, some people opt for a radius proxy deployment, where ICE proxies the request to another radius server. And this allows ICE to assign the SGT and be the administration point for the SGACLs. Some people love this. So single administration point is the pro. The con is it's more complex for load balancing, because you have to scale the proxy layer and you have to scale the layer behind it. Some people hate that, and so they want to go to a delineated model where we delineate the authentication just to the generic radius server. Any radius server can assign an SGT through a Cisco vendor-specific attribute. It's just a string. Now, the most notable thing about that string is you will see 0064. That is hexadecimal. So you are converting for the decimal representation in the UI to a hexadecimal representation on the wire. That's the downside. You are doing that manually. So the pro, though, is that you have discrete scaling probably already established for those radius servers, and the only thing you have to introduce into the environment is the download from the Identity Services Engine. So remember that CTS authorization list? This is how we can split the two environments. And here's a relative example. What's in blue is telling the device to download from ICE. What is in green is telling them to authenticate the users via a normal radius server. Next question is, what about Forescout? What about Packet Fence? What about overlay NAC solutions? So overlay NAC solutions are supported. They are reliant upon the vendor to integrate via PXGrid. And that is not because of anything we forced upon those vendors. We've actually worked with those vendors, and we went through a number of different technical options. And because of performance issues and other things, we have concluded that PXGrid integration is the best way to do that integration. So we are waiting for Forescout to ship their PXGrid implementation, but they will be doing so. What they will be doing is they will do their normal passive monitoring. Once they've made a classification of the endpoint, either through the application inspection or the probes that they send back to the endpoint, they will notify us via PXGrid of a new classification for the endpoint. We will then apply that to our authorization rule, and we will send a notification to the device of the new SGT. All of the identification, all of the authorization is being done in the system. The only thing we're doing is using a MAC authentication bypass handle. We're not actually authenticating any MACs. We use the handle as a way to assign the SGT to the switch. So that has already been tested at a couple customers, and they will be shipping that in their next release. I do not have specifics on when that is. So we've covered the base set of patterns. Now we need to apply those patterns to a WAN environment. So in a hospital or in a healthcare environment, we had a very simple set of use cases. I needed to separate the medical devices from the administrative devices, and I needed to separate my PCI devices from the rest of the infrastructure. But they did not have a refreshed infrastructure. They did not uplift their aggregation layer. They had not refreshed their WAN. So they were not ready to do end-to-end TrustSec. So they were asking me, do we have a way that I can separate these things without having to have TrustSec everywhere? And the answer was yes, they could. And the reason was they had done an access layer refresh, and they had bought 3850s. So what we were able to do was we were able to go in and we were able to classify the majority of their enterprise via a summary address that we had advertised to the edge via SXP, right? So I would use a 10008 to represent the majority of the enterprise. And just that single prefix represented about 25,000 endpoints. And I could write policy against it. Because what I really wanted to do was only elevate the privilege of the PCI devices and the medical devices and deny them access to that prefix that was not a specific match. In addition, I wanted to write known to known rules where medical device to medical device was permitted, but medical device to the summary address was denied, or an unknown address was denied. In addition, I wanted to have a way to classify quote-unquote internet traffic, basically anything that originated outside of the administrative domain. And the simplest way to do that is to use what we call a default route classification at the edge of the network. Now this exists on iOS X, XE 1611 switches and routers that are supported on those platforms, as well as on NXOS. There's one restriction: you must have a default route on the device that is doing the classification as well as the enforcement with this mapping, okay? But it does allow you to map 000 to a number or an internet SGT and write policy against it. So they wrote policy, medical devices, internet, deny. That bit them in one scenario. Has anybody ever had an MRI? Anybody been in an MRI machine? If you had, they'll give you some headphones, right? And you'll listen to music. Guess where that music comes from? iTunes. So we had to put in a proxy and say permit, iTunes. But we could do it. So this works very, very well, and it is available, and it's a way to classify the internet. But what they did, and this was a fairly long time ago, they decided to use what is called an SXP reflector design. So they would advertise the routes up to an SXP reflector, which would then advertise all of the IP to SGT bindings that were relevant back down to all of the access layer devices. So you'll see in the table in the top, I have 3 devices, but only 2 of them have SGTs. So when that access layer device would send that to the reflector, I only send the 2 IP to SGTs in the environment that have an actual SGT assigned to them. If I do not, the summary SGT 10.00/8 at the bottom of the table in the upper right is where I will enforce policy to any enterprise device. And then I will reflect that back down to the access layer. So at this point, I have a table that is relevant to all of the access layer devices. And it was less than 12,000 entries. Why is that significant? Because that is the maximum size of the IP to SGT table that you can hold in a 3850. But I'm going to show you that how the ingress device was doing ingress filtering using this technology. And it scaled better than writing it all out in source dest IP ACLs. So I would send a packet into the device. I would do the normal lookup. Do I have a source address? Do I have a destination address? In this scenario, I had exact matches of a medical device user going to a medical device user, so I would say permit, right? I'm at the ingress, I send that out, and it is permitted. And I'd have the same table at egress, so it would be permitted, right? Now, if I was a user that was not in the table, I didn't get a specific IP to SGT assigned to me, what happens is I would go look in the table, and it is a longest prefix match. So I have a /32, I will find it first. In this scenario, I do not. I fall all the way through to the 00/8. That is a non-medical device. It is classified as an enterprise user. So I am an enterprise user as the source. I look at the destination, I see that as a medical application, and I look at the policy and it's a deny. So this is how I can use this summary SGT to do ingress filtering at the medical environment. They also had a consideration. Because they were using the reflectors and were using loop detection, without this bug fix, I would build a topology of every path through every n-1 leaves. So if I had 200 leaves, I would build path information for 199 of them, which tended to make the SXP table very, very large. So large that it would crash the switch. So we had to implement this bug fix on the reflectors that limited the length of a path that you could send to the peers. So you can see that I have S1, R2, S2. That's 3 hops through a topology. So I have a limit here where I will only import and export paths that are greater than or equal or less than or equal to 2. So basically what it means is when I advertise that down, I strip anything off that is too large, and I only populate the peer or the access layer with an IP to SGT that has a path length of 2. So that keeps the memory of the leafs within sufficient bounds and allows you to scale out the environment. So This is the normal SXP configuration that you saw. One of the things that was interesting about their environment is they did transition to inline tagging on some of their routers. One of the things you'll note in the configuration, I have the CTS manual, and then I have a statement, no CTS policy or role-based enforcement. Why is that? Because if I am at a midpoint in a network where a router normally is, and I'm enforcing some policy, typically the return traffic, and I'm sending a packet out, and I send an SGT and I cannot derive a match other than a .8, like if it's going to 11.0.0.8, I may have a policy against the unknown SGT. If I have the unknown SGT policy defined, I will drop that traffic at a midpoint. You do not want the midpoint to drop that traffic. Or if I have a default deny, remember my warning about default deny? I would also drop the traffic. By turning off enforcement on any infrastructure link, I avoid that situation. So that's why it's a standard part of my presentation that we must keep the inline tagging links not doing role-based enforcement. So I mentioned the 12K limit on the 3850 because of ways that we're doing the memory allocation in the 9300. The actual limit inside of the 9300 is 10K IP to SGT bindings. There's also a couple other things that you want to be aware of in the switches as you're looking at scale. One is the total number of SGTs you're protecting. Before 17.1, we could only have 255 unique SGTs on any one given device. And that was a limitation when you were doing an aggregation layer, as an example, or a border router enforcement in SDA. That has since been increased in 17.1 to 4,000, which is typically much higher than the average scale of a deployment. So we're very confident that we have proper scale there. So you have to be aware of that limit. You have to be aware of the IP to SGT limit on every platform. We have documentation in the presentation in one of the hidden slides of the matrix that documents all the scaling of IP to SGT on every platform. In addition, you want to look at the ACE entries. Now, we reuse ACE entries per SGT DGT, right? So if source SGT1 going to destination 2 equals deny, and source 3 is going to destination 4 equals deny, that's one entry in TCAM. It's not two entries in TCAM. So that's how we get some more efficiency out of it. So you want to monitor that. And finally, you want to monitor the SGT_DGT. That is what we call an SGT DGT hash index. It is roughly equivalent to the total number of cells in the policy matrix that you have downloaded to the device. If you populate a matrix with a bunch of denies and a few permits, it is possible that you will overload that SGT DGT on an access layer. So it's something that you need to monitor. You can look at this monitoring information via netconf yang and have what is called streaming telemetry, stream this back to a collector. So you don't have to go out and collect this information. We'll just send it to you, and you can put it into a database like InfluxDB or something like that. So the healthcare organization started hitting scale limits as they started to grow their deployment. So they moved from access layer filtering to router filtering. So all they did in order to do that was turn on inline tagging in all of their remote sites, and then starting to do the north-south or the east-west filtering between the branches on the routers. The routers, as an example, a 4300 can support 135,000 IP to SGT bindings, so it scales much higher than the switches. So once they exceeded that 12K limit of the 3850 and needed to go to 25,000, they moved the enforcement of branch to branch or branch to data center to the routers. Anything inside of the branch was done through normal filtering decisions, right? So they evolved the deployment from an ingress filtering to a partial midpoint filtering because of scale. And over time, as they worked through it, they started to work farther and farther because of scale, right? So the table reflection was done now via ICE, and shared to the routers. Because since they reduced the number of peers on SXP from the access layer to the branch, there was a smaller number of peers that could fit inside of ICE's peering capability. ICE can only do 200 peers with 2 PSNs or 400 with 4 PSNs doing SXP. That fit well within their environment. So they were able to do router ACLs with ICE as the speaker. And so any north-south traffic got filtered at the router, and any east-west in the branch got filtered at the egress switch. Standard configuration. This is an example of how you configure the routers. You do turn off enforcement on the routers in the same way that you do the switches. Port channel support is supported, but you must put this configuration on the member ports, not on the port channel itself. So that's a detail. It's very much like CDP, LLDP, PAGP. It's a layer 2 function. So you want it on the member port and not on the port channel interface itself in order to enable inline tagging. So at this point, when people move to inline tagging, they ask a very simple question. How do I know if I'm tagging? So the simplest way to know if you're tagging is to turn on a NetFlow monitor. Even if you're not exporting that monitor anywhere, if traffic comes through the device, especially the routers, it's very simple to do, we will show you a local cache. So you can quickly answer, am I tagging, by looking at a NetFlow monitor that includes the match keywords for the source group tag and the destination group tag. And so it sort of looks like this. Now a question, I've highlighted the source group tag is 30, but the destination group tag is 0. Why is it showing 0? Anybody? Sir? So the statement was we were matching on the ingress interface, and we are seeing the SGT inline on the inline interface, but the router's a midpoint, so it's forwarding the packet through it. It does not know the destination group tag, so it reports it as 0. Now, the key thing is when you use something like StealthWatch, you will do flow stitching, and you will see the source and the destination tag in the flow collector itself. So that's because it will take the flow from the router, it will take a flow from the destination, put those together, and you will get a display so that you have the TrustSec source and destination SGT inside of the collector. This is just an example. Other collectors, Plixer as an example, also use the SGT from the NetFlow record to do reporting and eventing and alarming. Because you can build an alarm between source 1 and destination 2 tags, and if that is a deny, but you see traffic, you can generate an alarm because that's an anomaly against the policy, as an example. So that's where it can be used. There are also SXP and inline tag parsers for Wireshark that you can load via Lua. So you can actually do parsing of this in sniffers, no problem, because it's all published specifications. So in the routers, we do have some very robust information like I showed you earlier in the switches. At this point, people are saying to me, like, okay, it's great that I have this log keyword, and it's great I have these counters, but how do I centrally collect that and do anything useful for it? At the moment, you need to sort of do it yourself at the moment. And what we basically recommend is that we collect counters via that streaming telemetry that I talked about, where periodically I will just tell you what the counters are through netconf-yang. And we will want to use the log keyword for any syslog that you need, and then you're going to need to put it into a data storage, right? The typical data stores that I have helped my customer build are Elasticsearch for syslog and InfluxDB for the counters. And it's purely because of the reporting interfaces on top of it that you can build, and you can build analytics reports, because what we need to be able to do is when we're looking at a log that comes out of the device in the top in the white, it's unstructured data. It's very hard to search on. It's very hard to do anything useful or build analytics against specific subsets. So what we need to do is run it through a parser and turn it into structured data. Now, some companies like Splunk do this for you. Elasticsearch does it for you, but you have to build the filters yourself, right? But once you've turned it into that structured data, and once you've collected the counters and they pop out in a structured JSON format, what you can start doing is you can start looking at the intersections in the activity against any given intersection of logs or counters in the environment. So this is actually from my lab. The little dip in the event in the middle is when my developer decided to reboot the switch when I was taking this snapshot. So that's expected behavior. It's nothing. But the spike in the graph on the right was actually when we fired off, if you're familiar with Kali Linux, attacks from Kali Linux that went into the system and were being denied in the system. So it immediately triggered an operator exercise. This was a red-white exercise. The operator actually was using that graph in the environment to go then drill down into more analytics. He used Stealth Watch in that case, and then finally AMP to understand why we're seeing this spike in policy violations. So this is a way that you can start doing this ACL and this policy monitoring. The intent for Cisco is to move this into DNAC. So if you have any interest in having Cisco providing a monitoring tool for this, this is an example that we can talk to you about and build requirements for DNAC. So over time, the scale for this medical environment became hundreds of thousands of endpoints, and even the routers could not actually scale using SXP. So at that point, they had refreshed their access layer, they had refreshed their aggregation layer, they had refreshed their routers, and they were ready to transport the tag natively across the network. In their scenario, they were using public transport, internet transport, so they chose DMVPN versus GetVPN. So the same principle I'm going to show you in scaling here can be applied to SD-WAN in the second half of the year, when we will be able to do inline transport and SD-WAN. So basically what that means is then they only had to classify the data center and communicate SXP to the data center, to their electronic medical records system. So inside of the DMVPN, we'd carry the tag all the way to the egress at the data center. We would filter any east-west traffic in the site, still handled by the switch, but between the sites, the inline tag would go across and be filtered at the egress point at the opposite end branch. So we got, for the most part, almost infinite scale, but because we started to move to inline tagging, and the only IP to SGTs that we had to worry about was in the firewall in the data center. So inline tagging with DMVPN is actually configured on the GRE interface, and it is a simple command, CTS SGT inline. You configure that on either end of the DMVPN interfaces, and we will automatically negotiate the tagging interfaces and tell the central server that the peer is TrustSec enabled. So we will not send a tagged packet to a peer that is not enabled for inline tagging. So it is an easy way to incrementally roll out SGTs on top of DMVPN in a way that allows it to be sustainable through the environment. Finally, the data center. This is the place where SGTs typically need to interoperate but are not natively deployed. And the primary reason for that is because the primary path to enforcement inside of workloads is either an on-prem solution like ACI or a cloud infrastructure as a service. SGTs used to be supported in widely deployed Nexus 5K, Nexus 7K. They are not supported in Nexus 9K standalone at all. They are hardware capable, they do not have the software to do it. It is a decision by the Nexus 9K team that if you want to consume a policy construct, that you use ACI. That is a marketing decision. If you would like to change that, I encourage you to talk to the Nexus 9K product team. So the way this basically works is that we federate the controllers. So ICE is the controller for SGT, APIC is the controller for ACI. I basically reach out from ICE to ACI and I pull information. I pull the EPG and the IP of all of the devices within a tenant, right? So we will create a table inside ICE of EPGs with an appended name, even though that in our domain they will be an SGT, and the IP address. So we will have a table available to advertise via SXP. In addition to that, we write our IP to SGTs into APIC but convert them into EPGs on the layer 3 out of the tenant. If anybody's familiar with ACI, a layer 3 out is your communication to the outside world. So what happens is when I send that to APIC, it then downloads that to the leaf. So I'm downloading IP to EPGs to the leaf. There are limits to how many IP EPGs the leaf can have, right? And we're fixing that later this year, where we're going to move from just an IP to EPG to an inline tagging scenario. But what basically happens is I tag through the SGT environment. When it reaches the edge of the SGT environment, it reverts to plain Ethernet IIP, right? We strip the tag, just like we did with the firewall in the earlier example. We send that into the ACI fabric. At this point, the ACI fabric reclassifies with the IP to EPG and submits it to their policy, right? Whatever policy they have for that EPG going to a workload is implemented. So in that way, we now have a federated function between the IP to SGTs in ICE and the IP to EPGs in ACI. And you can implement policy for end users as classified by ICE or profiling. So what's it sort of look like? This is just an example of the SGTs we have in DNA Center, and this is what they look like in APIC. We append SGT into the name in APIC so that you know exactly where it was derived. In the same scenario where we're pooling, we will append EPG to the end of an application profile name for the EPG. So the key is that we can have 250 unique EPGs that we can pool, but the most significant thing is that we can have 64,000 IP to SGTs on any leaf for any tenant, right? So in this scenario, you are limited to 64,000 IP to SGTs that you can advertise into an ACI domain. So we have the ability to advertise some SGTs, but not others into the domain. So you do not have to flood all IP to SGTs into the API environment. It's recommended to use 2.4 patch 6 and above. So another way to do policy that will have more scale than this, remember, as an example, a ASR1K can scale to 170,000 IP to SGTs. If we're pulling the IP to EPGs out and we're only sending those IP to EPGs to the edge, to the firewall, which can support 1 million IP to SGTs with an ASA, or an ASR, and I'm tagging in the infrastructure, I can get very high scale at the edge of the SGT domain, much higher than I can in the ACI domain at the moment, right? So I would send the packet across, I would derive the SGT from the packet, I would derive the destination that is representative of the EPG on the border, and I would drop it there. So this is just an example of what an EPG looks like inside of ICE. You see that we append the EPG to the end of the SGT name. That's all it is. So these are just some examples. In the next slide, you can see that we used a reserve range of SGTs, 10,000, and those represent EPG names on the right, where that 10,000 are all the application profiles that came from ACI. So there's just an example to show you the interoperability. And the same information gets communicated across PXGrid, so you can see this in external systems like firewalls, or in this scenario that I show you, this is the 10,000 EPG represents it showing up in StealthWatch. So you can use this to enforce policy on firewalls like FTD or ASA or other third parties. So at the end of this, we always have to talk about cloud. And basically at the moment, you can solve cloud workloads with some function. It is not automated function as of yet. We're hoping to build that. But basically, I had a scenario with a customer where they wanted prod and dev workloads separated such that enterprise users cannot access dev workloads. In a normal environment, if we had a new business app that needed to be turned up, I had to create a ticket, I had to have a VLAN created, I had to go give that to security so they could build an IP to security rule, and I had to put it in the firewall manager, and then I had to push it to the edge control points, right? And in that scenario, in many instances, an employee would go to a firewall that had been updated, and they would have their traffic denied. But a developer would say, I don't want to do any of that. I'm going to create the workload in the cloud, and the firewall would never have a policy for that, and the developer would actually put it up, and an employee would actually access a dev workload. Has anybody ever had one of their production users touch a dev workload on mistake? Anyone? Few people, right? It happens. And in some scenarios, a regulated environment like they were, because they were a bank, that must have a mitigating control. So the way they did it was they integrated with an orchestration tool, such that everybody that needed to turn up a workload, whether production or dev, had to go through an orchestration system. So the orchestration system would create a ticket, it would go to the orchestrator would touch ICE via API and create an IP to EPG. As soon as the IP to SGT was created, it would automatically flood that to all of the firewalls, either through SXP or via PXGrid. And so they went from a change control window to get a new ticket opened and deployed for a dev was anywhere from 24 to 72 hours. With this automated system and the automation via APIs, they literally did it in milliseconds, because the IP to group mapping for the workload would get turned up as soon as the developer touched the environment. As soon as the developer touched the environment, the policy rules were in place and the employee could not access the data, right? And it was literally milliseconds. We measured it. We had to prove it to the auditors. So what we did is we used REST APIs from ICE to do this. So these are just examples. There's an example script on the GitHub that you can use if you want to see how to do this yourself. And basically, we're able to define an IP to SGT via the REST APIs, have it appear in ICE, and then communicate that via SXP and PXGrid. Where this comes into play, as an example with AWS, is we can't put the CSR or a control point in front of the workload, so we typically do the filtering at the transit routers that typically are CSRs or other virtual devices like a router that can do the enforcement. So what it looked like when we had a user in the environment, if they were going to their normal data center, we'd have the workloads defined, we'd have the table for the users and the workloads aggregated, and then that would be reflected out to the control points, and the control points would have the aggregated tables. These are routers and firewalls, very large scale, especially in virtual form factors. And so any communication either to the legacy data center or to the new cloud IaaS environment would immediately be subject to a policy enforcement. Do I know the source? Do I know the destination? What's the ACL, right? So that's it. You made it through. That's 2 hours of rapid fire content and me making terrible jokes. In summary, I want you to understand that we can deploy this. What I gave you were real life examples of how customers have deployed this in their network. In addition, we're continuing to innovate to get this deployed in your environments in a reasonable way that is operationally scalable. And you can do it. That is the one thing I hope you got out of this, is that this is a feasible set of technology that you can deploy. I was asked to put in a reference to other sessions. All these sessions have, for the most part, already occurred, except the break sex tomorrow. You can go to these sessions because they're relevant to the things that I have talked about today, either ICE with Duo for Zero Trust or other sessions on how to do filtering with SGTs. So here are some reference links. One thing that I would beg you, we do take the scoring at Cisco Live very seriously. I'd like you to rate the session the way you think it was valuable to you. They rate the speakers on whatever you rate the speakers on. If we get a good enough score, we get invited to come back. I've been here long enough, I already got a good score. Please give me your feedback. I want you, more than anything than rating the session or rating me as a speaker, give me feedback in the comments to help me understand what was relevant or not relevant for you. If there's anything that you can do for me, that's the one thing. So with that, I would encourage you to continue your education, and I am done for the week.